Welcome. All right, so we're going to go over the answers to those questions. Given the function, decide if it's continuous or not. If it's not continuous, then state the reason it's not. Right? So when you're determining a function is continuous, right, you have to make sure that all three of these requirements are met. And when it's not continuous, which one is not met? And this is sort of a hierarchy. Right? So if a function doesn't exist for all a, right, you're not going to be concerned if the limit exists or if the limit is equal to the value of the function, because your function is not defined for all values. So if your function is not defined for all values, you stop there. If the function is defined for all values, but the limit does not exist for all values, you stop there. Right? So if the limit doesn't exist for all values, right, it's certainly not going to equal the value of the function for all values. Right? If you meet the first two, then you go to the third one. All right, so here's our greatest integer function. And, oops, and it doesn't want to move. And so it's a little counterintuitive why that's the greatest integer, because you look at it and you go, well, gee, if it's anything between 0 and 1, that's a small integer, it's only 0. So it's sort of like the greatest integer that there is in the greatest integer there is in our answer, in the y value, and that's what the graph is. So for instance, anything between 0 and 1 is going to be 0, because the greatest integer in anything from 0 to 1 is 0. Right? You've got 0 and then you've got some decimal. Right? And then once you get to 1, your greatest integer is 1, because now you're 1. And you're 1 for everything until every little bit, every little decimal, 1 point every decimal until you get to 2, and then you jump up the next one. Right? The least integer function is the other way. It's 1 less than the integer you have. So for 0, you jump up to 1. Right? So you round up to the next integer, and that's the least integer. So it's a little counterintuitive. Right? So, well, this has a jump discontinuity. So that kind of blows continuous, doesn't it? Right? So sometimes the fact that you are not continuous is kind of obvious. Right? So then we need to figure out why. F of a does not exist for all a. Well, for any integer that you plug in there, right, you've got a place, right? So it's going to be 0, right, until you get to 1, and then it's going to jump up again, and it's going to jump up again, right? So can't really say doesn't exist for all integers. The limit as x approaches a of f of x does not exist for all a. Right, so let's take a look at that one. Right, so if you're in between two integers, right, so you're not at an integer value, right? So for instance, 0.5, right? From the left-hand side and the right-hand side, you're going to approach 0. And if you're anything on this little segment in between those two endpoints there, the limit and the value of the function is going to be the same. If you're an endpoint, right, the value, the f of a exists, and the limit as we approach from the right exists, right? So the endpoints are good, but the left endpoints are good, right? They're continuous because the right-hand limit and the value of the function are the same. But what happens at the right-hand limits? So left-hand limits are good, but then at the right-hand limit, whoops, it all blows away, right? So here, from the left-hand side and the right-hand side, just not the same. So we have found our problem here, and it's this one. The limit of the function is from the left. Oh, we can't even see it. Looks like part of the f there. So the limit as x approaches a from the left is not the same as the limit as x approaches a from the right. And that's true for every integer value, right? At any integer. It's fine in between the integers, but not at the integers, right? So because those limits don't exist from the right and left-hand side, we're not continuous. Or the greatest integer is not continuous. Given the function, decide if it's continuous or not. If it's not, state the reason. y equals the absolute value of x. Well, there's just no number you can't take the absolute value of. So this is not a problem. The limit of f of x as x approaches a does not exist for all a. I just happened to choose one point there. I could have chosen any point, even the vertex. From the left and the right-hand side, I'm approaching the exact same value. And that's true down here as well, right? From the left-hand side and the right-hand side, approaching 0. Right? So, and actually I'll write that in there. So here, the limit as x approaches 0 is 0. And of course, the absolute value of 0 is also 0. And that's going to be true for every value, every x value you could possibly choose. Right? So the limit does exist for all values, and it's exactly the same as the value of the function. Right? So that means this is continuous. Let's look at the next one. Right? So y equals 1 over x. Of course, it's a rational function. It's got an infinite discontinuity, so that's just going to take care of continuous if you've got an infinite discontinuity. And so let's go through our hierarchy. We're not going to go any farther if one of them is false. All right, so what value can you not plug in for 0? Well, f of 0, excuse me, what value can you not plug in for x? Did I say what value can you not plug in for 0? If I said that, I'm not going to rewind to hear myself, but what value can you not plug in for x? Of course it's 0. So f of 0 does not exist. You can't plug that value in. So since f of a does not exist for all a, our graph here is not continuous, and we're stopping at that one. And then the last one here, we have a piecewise function. Given the function, decide if it is continuous or not. If it is not, state the reason. So this one here, a graph, is very helpful. Of course, we can factor and reduce, which means that our rational function for one part of our piecewise function here is simply a line. Right? It's a line that has a hole in it, right? Because we can't plug in -1. Right? So that's hence the reason it says x not equal to -1. There's a hole there. Right, but we've filled in our hole. We've got, when x equals -1, our function is 2. Right, so now let's determine whether or not our graph is continuous or not. So to do that, we have to go through B, C, and D. F of a does not exist for all a. Well, if this weren't here, I was going to cover it up with my hand, like you could see that. So if this weren't here, right, if that were gone, then we'd have a hole in the graph, and it would not exist for all a. But we have plugged in the hole, right? So here, this is a no, because the hole is plugged in. In a sense. All right, so the hole, I shouldn't say the hole. First of all, that's the wrong hole. The hole. It's not exactly plugged in, but there's a point for it, right? So we have a hole. I shouldn't really say the hole is plugged in. The hole's still there. So there's a hole, but, and I should say where the hole is. There's a hole at x equals -1, right? But we're covered there because f of -1 equals 2. All right, so not a problem in terms of f of a not existing. The limit of f of x as x approaches a does not exist for all a. I happen to choose right by the hole, but I could have chosen anywhere on that line. It's just a linear function from the left-hand side and the right-hand side. We are approaching the same value, right? So our limit does exist. The limit as x approaches any a from the left equals the limit as x approaches a from the right, right? So that is not a problem. The limit of the function is not, the limit of the function as x approaches a equals f of a is not true for all a. Well, we just listed it up there by b, didn't we? And you can see it on the graph. right? So the limit as x approaches -1 of our function does not equal f of -1. That's the problem right there. And so, of course, we're not continuous because the limit and the value of the function are not the same. So, if you didn't do as well as you'd like, that's okay, so long as you understand them now. All right, so if we're going to find and identify points of discontinuity of y equals 3 divided by x minus 1 squared. So what value can you not plug in for x? Well, you can't plug in 1, right? Got a problem with 1. And that creates a vertical asymptote, which is an infinite discontinuity. Right? So don't tell me if I ask you what kind of discontinuity, don't say vertical asymptote, right? You say infinite discontinuity. Goes on and on forever, right? There's just no way you can plug in a 1, right? And our function's going to get closer and closer to 1 forever and ever, but it's never, we're never going to be able to have x equal to 1. And here is our greatest integer function. Got tongue-tied there. Greatest integer function, right? And so we're looking at where it's continuous and discontinuous. Right? So this is a nice one to do that with because it's got so many points of discontinuity. Right? Continuous. Notice the bracket. Right? Our function, the greatest integer function, is continuous at the end points. Right? So each little piece at the left end point is continuous, right? So because the limit as x approaches 0 from the right, our right hand limit, and I already wrote it down right there, right? So the limit as we approach from the right does equal the value of the function, right? So the limit as x approaches 0 from the right is 0, and f of 0 is 0. And that would be true for 1 and 2 and 3 on the left-hand side, right? But notice then on the right-hand side, not so much, right? Right, we're not continuous on the right. So for each little piece at the left-hand side is continuous, and then it's not continuous on the right-hand side as we come from the right. So all the integers, it's discontinuous. Right, 1, 2, 3, 4, and so on. And I'm going to take a break and start a new podcast. And we're going to take a look at removable discontinuities. Right? So see you in the next podcast. Bye for now.